Welcome to my video lessons. Right, see, the main objective of this video, in this video I am going to explain about the single phase full wave control converters or rectifiers. See here, what is a converter or rectifier means? It is rectifier is a device. It is going to it is converting the AC signal to the DC signal, and see, in this it is a controlled rectifiers, controlled converters. That means the output value can be controlled in these circuits, right? Circuits, single phase full wave control converter using resistive load, and single phase full wave control converter using RL load. I will discuss these two topics in this video. That means a single phase full wave control converter using resistive load and using resistive and inductive load. See, once we will recall, I will recall my previous video session. In that video I discussed about the single phase off wave control rectifiers, right? That means it is off wave control rectifiers. Single phase means depending on the line, there are the two types, single phase and three phase. So here we are discussing about the single phase. In my next videos I am going to discuss about the three phase rectifiers, right? What is difference between off wave control and full wave control converters or rectifiers, right? In already we discussed about this off wave control rectifiers. In off wave, only for the complete cycle, only half of the signal is going to convert into DC, and that signal only can be controlled. See here, the main controlling elements in the control device circuits are thyristors. If you recall this off wave controlled rectifier with resistive load or RL load or whatever it may be, freewheeling diode, the main element here is thyristor, and in off wave the number of thyristor elements are only one. One SCR is used in off wave control rectifiers. And what is the difference between this resistive load, inductive load, and using freewheeling diode means? In the resistive load, what is happening? It is 0. The signal will be 0 after pi radians. Whereas in the inductive load, we are getting a negative output voltage after pi. That means until the second negative cycle. That means this is due to the energy in the inductance. Until the stored energy in the inductor is dissipated through the load resistor, this SCR is still in the conducting mode. In that case, the output is in the negative form. That is the case of inductive load, and this is the drawback of in this inductive load. We are getting the negative output voltage, and due to this inductor, what is happening? There is a flyback effect. Some loading effect is some voltage is output voltage fed to the input. This is avoided by using a freewheeling diode or commutating diode or clamp diode, snubber, whatever it may be. See, this is with a freewheeling diode. There are many names for this freewheeling diodes. This freewheeling diode is connected across this RL load. It is preventing the flyback effect, and the main is it also improves the power factor. Right. Waveforms of different points in the circuit for voltage and currents we discussed. For every circuit we discussed about the input and output waveforms, and in the freewheeling diode the current is continuous. If you observe the output waveforms of single phase off wave control rectifier with freewheeling diode, in that the current is continuous. The main advantage is it avoids the freewheeling effect, and it improves the power factor. This is about the previous class. Now we will discuss about the single phase fully controlled converters. See, fully controlled, what it means? Fully controlled converters. Generally, a converter is a device, it is converting to one form to another form. Here this circuit is converting AC into the DC, and the name here it is fully controlled. That means here the complete cycle is converting into the DC form. The complete, that means a positive and negative of cycles are going to convert into the DC. That is the meaning of fully controlled converters. And single phase already I explained what is single phase and what is three phase. The line here is single phase. Generally the from the power stations the electricity will be, the connection will be either single phase or three phase. Single phase is generally used for households, and three phase is normally used for industrial applications. That means if the load is heavy, in that cases we need to go for the three phase. If the load is less, then we can choose the single phase single phase lines. Right. Single phase fully controlled converters. Here the conversion is for both the positive and negative of cycles. Right. Here in this the controlling devices are two SCRs and a single phase center tap transformer are used. In the fully controlled converters, what are the required elements means it needs two SCRs because it converting two of cycles, positive cycle and negative cycle. So for this we need two SCRs. And one more thing, generally we will use the transformers for step up and step down operations, and that means high voltage to low voltage. Right. Here the transformer is a center tapped transformer. We are using a center tapped transformer. A single phase center tapped transformer are used in this fully controlled rectifiers. This fully controlled converters are also called two pulse converters. These are also called two pulse converters. Now, to design this circuit, what are the main required elements? It needs two SCRs and a center tap transformer. This is the block diagram of this fully controlled converter. Right. Just now I said that it needs two SCRs. Here you can observe T1 and T2. These two are the two SCRs and one center tapped transformer. We know the function of the center tap transformer. Say this is the primary of the transformer and this is the secondary of the transformer. Say for the positive of cycle, this A is positive with respect to the B in the center tap. Generally here it splits positive, negative and positive, negative. With this A is positive with respect to the B, and for the negative of cycle A is negative. Here we will get negative, positive, negative and positive. A is negative with respect to the B. A is negative with respect to the B. Right. That means B is positive with respect to the A. Right. This is about the center tap transformer. And two SCRs. Anode of the SCR1 is connected to the point A of the secondary of the transformer, anode of T1. Right. Here anode of T2 is connected to the transformer secondary of the transformer at point B. And here the load resistor R is connected. Right. This is the construction of the circuit, fully controlled converter. has 2 SCRs and 1 center tapped transformers. Now we will see the working operation of this fully controlled converter with resistive load. See, these are the waveforms for this circuit. Before going to this waveforms, once see, if A is positive for the if the input is positive of cycle, that means A is positive with respect to the B. A is positive means for T1 SCR, T1 thyristor, anode is positive, and B is negative. That means for T2 anode voltage is negative. See, already we know that SCR is a unidirectional device. The conduction is only one way, that is from anode to cathode. When the anode voltage is positive with respect to the cathode, then only it conducts. That means here T2 thyristor is turned off. It is not in the conducting mode, it is off state. T2 is in the off state during the positive off cycle. Now here T1, anode of T1 is positive. But we know the function of this SCR. To trigger this SCR, it requires some time, that is delay angle. After some delay, then only it will be triggers. It comes into the on state. There is a forward blocking state, though it is in the forward mode, but there is some forward blocking state. In this state, it only flows, only a small leakage current flows. The current is very less, a small leakage problem. Thus, whenever this anode voltage reaches the breakover voltage, then only the device triggers. The SCR triggers. So it needs some time. That time delay is called firing angle or delay angle. After this firing angle, the device is in the on state, fully conducting mode. It is in the on state. That means whatever may be the input voltage applied at the primary of the transformer, that will be appears at the output of this voltage across the resistor, VDC, voltage across the resistor. Now come to the second case. For the negative off cycle, A is negative with respect to the B. That means at A there is a negative value, at B there is a positive value. A is negative, that means anode of thyristor T1 is negative. That means this is completely in the off state. And B is positive. When B is positive means anode of T2 is positive. That means it is in the forward mode. But still here also, to trigger this device, it needs some delay angle. That is after some time only it comes into the conducting mode. Right, up to this we know the function, and that means when after this firing angle, the current flow direction is like this, to the again through R to the center. Now observe the waveforms. For positive off cycle, firing pulses. After this alpha firing angle, this T1 is in the conducting mode, and the output and current I0 and V0 are like this. After firing angle, V0 is equals to Vi. Here you can observe V0 is equals to Vi, and I0 current is also flowing until that means up to positive offside. First positive offside until the pi radians. Pi radians. Now, when at pi there is a output reversal or input voltage reversal. That means for negative off cycle, T1 is off, and T2 is on. T2 is on after the firing angle. This is pi plus alpha. Pi plus alpha. Means with the T2 thyristor, again V0 is equals to V in with positive voltage. Right. This is the output waveforms for the fully controlled rectifiers. Output voltage and the input current. These are the output voltage and output current waveforms, load current and output voltage. More clearly you can see this. This is the currents of SCR1 and SCR2. SCR1 for positive cycle, the current is flowing through SCR1, and for negative cycles current is flowing through SCR2. And this is the output voltage. This offset is due to the delay in each of each SCRs. Right. Working of the circuit. See, during the positive off cycle of AC supply, during the positive off cycle of the input, what is happening? The terminal A of the transformer in positive with respect to terminal B, T1 is forward biased and T2 is reverse biased. T1 is forward and T2 is reverse biased. Initially they are in off state. See, T1 is forward biased and T2 is reverse biased. Before this, both are in the off state. After this positive off cycle, T1 is forward biased and T2 is reverse biased. When SCR1 is triggered, current will flow from terminal A through SCR1, the resistive load R, and back to the center tap of the transformer. For the positive off cycle, SCR1 is triggered and current is flowing from terminal A through SCR1 and the resistive load and back to the center tap of the transformer. But this is for the positive off cycle. Here current continues to flow up to the angle pi. The SCR will be in the active mode up to the pi radians. Right? So the current continues to flow up to angle pi. When the line voltage reverses its polarity, SCR will be turns off. For the negative off cycle, terminal B of the transformer is positive with respect to A of the SCR. That means SCR2 is triggered, SCR1 is off state. SCR2 is triggered at an angle of pi plus alpha. Current would flow from terminal B through SCR, through resistive load, and back to the center tap of the transformer, the bottom loop in the circuit. For positive off cycle, the closed path is the upper loop of the circuit, and for this negative off cycle, the current flow is in the bottom loop closed path. This is about the fully controlled rectifier. See here, in this negative off cycle also, the current continues till angle 2 pi. After that, the SCR is turned off. Here it is assumed that both thyristors are triggered with the same firing angle. The firing angle, that means the properties of each SCRs are same, the specifications. With that, the firing angles are same with the same firing angle, hence they are sharing the load current equally. The load current is equal for the two thyristors, because here we are assuming that the firing angle for every thyristor is same. Each of the input wave is applied across the load. Across the load, two pulses of current in the same direction. Here, hence the ripple frequency across the load. The ripple frequency across the load is twice that of the input supply frequency. Input supply frequency. Two pulses of current in the same direction. For each of the input wave is applied across the load. Across the load, two pulses of current in the same direction. Right, for positive and negative cycles, the current direction is same. With that, the ripple frequency across the load is twice that of the input supply frequency. Input supply frequency. The output DC voltage across the load, or the output DC voltage, that means VDC, it is equals to Vm by pi into 1 plus cos alpha. What is alpha? Alpha is a firing angle. And IDC, output DC current, it is equals to VDC by R. It is equals to Vm by pi R into 1 plus cos alpha. And RMS load voltage, it is equals to Vm by pi minus alpha 2 pi plus sine 2 alpha by 4 alpha under root of Vm under root of pi minus alpha by 2 pi plus sine 2 alpha by 4 alpha. Right, this is about the fully controlled rectifier with resistive load. Means after this after for positive cycle or negative cycle, this device either in any one of the SCRs will be turned off immediately with the phase reversal of the input. Again, other thyristor will comes into conducting mode after the delay angle. Right. Now we will discuss the fully controlled converter with RL load. Resistive inductive load. That means fully controlled converter means it also has two SCRs T1 and T2, and a center tap transformer, and the load here is R and L, resistor and inductor. RL load, the load is RL. Right. What is the difference between this resistive and RL load means in the construction part only the additional element here is inductor, it is in series with the load. Here the load is R and L. Remaining circuit is similar to this previous circuit, that means with R load, resistive load. Here due to the inductance, what are the effects in the output we will see. These are the waveforms. This is the input, positive and negative of cycles. See, these are the firing pulses for thyristor T1, and this is for firing pulses for thyristor T2. Output voltage V0 and low I0 waveforms. Here, before entering into this, just recall single phase off wave controlled rectifier with RL load. See, in that circuit, the V0 for positive off cycle, SCR is in the conducting mode after this firing angle, and up to pi there is a V0 is equals to V in positive voltage. After pi radians, after pi there is a phase reversal in the input, but still the SCR is in the on state due to the energy stored in the inductor, but the output is negative, this is up to pi plus alpha, that means until the energy stored in the inductor is dissipated through resistor, this SCR is in the conducting state, right. The same is applicable in this circuit also. Here up to this pi plus alpha, up to this V0 is up to pi, V0 is positive. From pi to alpha, pi to pi plus alpha, it is negative. After that, thyristor T2 is conducting, and up to 2 pi there is V0 is positive. From 2 pi to 2 pi plus alpha, V0 is negative. This is due to the energy stored in the inductor. Right? Energy stored in the inductor. This is the current waveform, output waveforms, load current I0. Here it is. There is up to after pi plus alpha, it is 0. Immediately it is going to charge flow. This is the load current of this fully controlled rectifier with RL load. The circuit function is same. Suppose here for the positive off cycle, A is positive with respect to the B, that means T1 is triggered, T2 is off state, right. Here until the up to firing angle, this T1 is also in the off state blocking mode. After this it comes into the triggering state, means after the firing angle the current is flowing through point A, through SCR and through RL load, right. For the negative off cycle, B is positive, that means the current generally flows point B, thyristor T2, inductor and R to the center tap transformer. But here for negative, when A is negative, generally this T1 should be off, but due to the energy stored in the inductor, still this T1 is in the on state. This thyristor T1 is in the on state until this T2 will be triggered, until T2 is comes into the conducting mode. This T1 is in the on state only. This is for the at pi to pi plus alpha radians. Similarly, for 2 pi to 2 pi plus alpha, this T2, though there is a negative value at point B, but this thyristor still it is in the on state due to the energy stored in the inductor. Until what time it is in the conducting mode, means until this thyristor T1 conducts. This you can observe in the diagrams. These are the firing angles for the thyristor T1, and these are the waveform pulses for thyristor T2. And this is the output voltage. After firing angle of T1 thyristor, there is a positive voltage, and still it is in the on state, but we are getting the negative value due to the inductor. And after pi plus alpha, T2 is in the conducting state. Up to 2 pi there is a positive voltage. From 2 pi to 2 pi plus alpha there is a negative voltage. And after 2 pi plus alpha, T1 is in the conducting state, on state, so there is a positive voltage again, and this is the current waveforms, right? Load current I naught working. SCR1 can fire into the on state at any time after Vs1 goes positive. After applying the positive half cycle, SCR comes into the on state after delay angle. Once the SCR is turned on, current buildups in the inductive load. Whenever the SCR is in on means there is a current in the inductor, means it starts charging. It starts charging and it starts storing the energy. Maintaining SCR T1 in the on state up to the period when Vs1 just goes negative. Generally, SCR will be in the on state up to the period when Vs1 just goes negative. Once Vs1 goes negative, Vs2 becomes positive, and the firing of SCR2 immediately turns on T2 and turns on the T2. The load current here is continuous or discontinuous depending on the inductance value. See, here there is no complete, if you observe the output waveforms, the load current is coming into the zero value and immediately it is increasing. This is depending on the inductance value. The load current may be continuous or discontinuous. The current is continuous, either discontinuous. It depends on the inductance value, right? The load current is continuous. When the load current is continuous, when it is discontinuous, means this load current is continuous until the inductance value is greater than its critical value. This load current is discontinuous if this inductance value is less than its critical value. So here we are assuming that the inductance is always larger than the critical value. That means here we are taking that means the load current is continuous. Here in this circuit, each thyristor conducts for a period of 180 degrees. Both the thyristors are triggered with the same delay angle. Each are conducting for a period of 180 degrees and with the same specifications, the same delay angle. Hence, the load current is shared equally between the two thyristors. So here VDC equals to 2 Vm cos alpha by pi. 2 Vm cos alpha by pi. See, this inductive load is similar to the full half wave controlled with half wave controlled rectifier with the RL load. The only here the conversion is for 2 cycles. That is the reason we are getting the positive voltage with small negative and immediately positive output voltages, and here the current is almost continuous but with zero values. This is depending on the inductance value. In this session I discussed about 2 circuits. That is mainly the topic is here single phase fully controlled rectifiers. What is a rectifier? It converts AC to DC. So fully controlled means it full cycle is completely converted into the DC form. Here this controlled rectifiers, the output value can be controlled. Here how it is controlled means by varying the firing angle. By changing the firing angle, the output voltage can be varied. Output voltage also varied means it can be controlled. This single phase fully controlled rectifier with resistive load and resistive and RL loads. Two circuits, R load and RL load. Here also there is another type using freewheel load, and the input and output waveforms of each circuit. Input and output waveforms for the each circuit we discussed. Let us some sketch. Fully controlled rectifiers are also called unidirectional converters, bidirectional converters, cycloconverters, and choppers. What is the answer? Fully controlled rectifiers are also called bidirectional converters. See, these fully controlled rectifiers are also called two-pulse converters. Two-pulse converters. What is two-pulse means? So both the it means two pulses, positive and half cycles we are converting. That is the reason it can call two-pulse converter, and bidirectional, positive and negative both are conducting. So bidirectional converters. Next question. A fully controlled converter implies a converter in which all rectifying elements are PN diodes. Rectifying elements are thyristors and diodes. All rectifying elements are thyristors or power transistors. Option D is freewheeling diode is used. See, a fully controlled converter, a controlled converter implies a converter in which what are the elements used? All rectifying elements are PN diodes. No, it is PN diodes are not used in the controlled converters. And rectifying elements are thyristors and diodes. It is also no. Right, no, wrong answer. And all rectifying elements are thyristors, either thyristors or power transistors. That means in the fully controlled rectifiers, the elements are either thyristors or power transistors. Option C is the right answer. All rectifying elements are thyristors or power transistors. Right. Question 3. Third question. Midpoint converters M2 connection are called dash converters, pulse converters, midpoint converters. Option A 1, option B 2, option C 3, option D 4. Midpoint converter M2 connection are called dash pulse converters. Fully controlled rectifier is called two pulse converter. Two pulse converter. Option B is the right answer. Two pulse converters. Right. What are the questions we can expect from this topic means? See, what we discussed is single phase fully controlled converter circuits. Right. Here in short answers you can expect what are fully controlled rectifiers. What is a fully controlled rectifier? Then this you can expect in short answer. Right. Draw the circuit for single phase full wave converter with RL load. Draw the circuit in the short answers. In some cases, draw and explain the single phase full wave converter with R load, and sometimes draw its input and output waveforms also. And in the long answers, you can also expect draw the circuit of single phase off wave converter with RL load. Sometimes only draw, sometimes it may be draw and explain, and also explain the waveforms of its circuits, or input and output waveforms. Generally, whenever if the question is draw and explain means you have to draw the circuit, explain the operation of the circuit with waveforms. At the time of explanation, definitely you have to draw the waveforms. Sometimes in short answers, draw rare cases, draw the input and output waveforms of converter circuits with R load or with RL load, like that. It is very rarely, but most frequently we can expect what are the fully controlled rectifiers, and What is single phase full wave converters? What is the meaning of single phase? With explain the circuit of single phase full wave converter with R load or with RL load. With RL, two circuits. This is about fully controlled converters. Single phase fully controlled converters. Here the main elements are SCRs. Here for full conversion for both positive and off cycle conversion, two SCRs are used with center tapped transformer. The another element here is center tapped transformer. This is almost similar to the full wave rectifier. Again, full wave rectifiers are two types using center tap and bridge. Because of center tap is bulky, we are going for the bridge. In bridge, we will use the normal transformer, but with 4 diodes. This is although the same case. Here it is transfer for center tap transformer with 2 SCRs. Each SCR conducts for one positive cycle, one for the positive cycle and another for the negative cycle. And this is about the fully rectifier, single phase fully controlled rectifiers. In my next video, I will explain about the 3-phase full wave control converters. Okay, I am going to end this session. Thank you.